About 2.5 billion years ago, the primitive process of glycolysis began. Later, as oxygen accumulated in the atmosphere, life began to probe the land. And survival depended upon the availability of large reserves of energy, far more than glycolysis could provide. In converting one molecule of glucose to pyruvate, glycolysis generates 2 molecules of ATP. However, these 2 ATPs represent only 2.2% of the available energy. The remainder is held in the pyruvate and NADH and lost as heat. In the second phase of cellular respiration, the Krebs cycle, more energy is released by metabolizing pyruvate. The Krebs cycle was named after British biochemist Hans Krebs, who traced pyruvate beyond glycolysis. Inside the cell, pyruvate moves from the cytosol through both mitochondrial membranes into the matrix. Here in the matrix, the Krebs cycle takes place. Pyruvate is a 3-carbon molecule, but the Krebs cycle uses a 2-carbon molecule as its starting point. So, an intermediate process, oxidative decarboxylation, is required to prepare pyruvate for the Krebs cycle. As pyruvate encounters coenzyme A, the complex kicks out 2 electrons, a hydrogen atom, and carbon dioxide to form the acceptable 2-carbon acetyl-CoA. The electrons in hydrogen are picked up by NAD+, forming NADH, an intermediate energy carrier. But it's the 2-carbon acetyl-CoA that we're going to keep an eye on. First, let's step back and take a simplified look at the Krebs cycle. The 2-carbon acetyl-CoA joins with a resident 4-carbon compound, producing a 6-carbon compound. Through successive reactions, 2 carbon atoms are given off. But it is the release of energy bundles that we're interested in, ATP and the intermediate carriers. That's the overview of the Krebs cycle. Now a more detailed look at the cycle will reveal how the energy bundles are generated. Acetyl-CoA hooks up with the 4-carbon oxaloacetate, producing the 6-carbon citric acid. Citric acid loses water to form aconitate. Then aconitate picks up water and is twisted into isocitrate. Isocitrate encounters an NAD+, forming the energy carrier NADH and oxalosuccinate. Oxalosuccinate loses a molecule of carbon dioxide, forming the 5-carbon ketoglutarate. Ketoglutarate hooks up with the ever-present coenzyme A and releases 2 electrons, a hydrogen, and carbon dioxide to form succinyl-CoA. Once again, 2 electrons and hydrogen form an NADH energy carrier. Standing by the succinyl-CoA reacts with an ADP and a phosphate, releasing coenzyme A, ATP, and forming succinate. Succinate encounters a molecule of FAD, and this reaction produces a newcomer, the energy carrier FADH2 and fumarate. Fumarate in turn reacts with water, and the product is malate. In the final reaction, malate encounters an NAD+ and produces the last of the NADH energy carriers and regenerates oxaloacetate. The Krebs cycle began with the prime player, acetyl-CoA, reacting with oxaloacetate. Through a series of 10 stepped reactions, oxaloacetate is transformed to several different reactants and is cycled back to oxaloacetate. In a single turn of the cycle, the energy carriers spun off were 3 NADH, 1 ATP, 1 FADH2, as well as waste carbon dioxide. The 2 carbon atoms that entered the cycle were expelled as carbon dioxide. So the purpose of the Krebs cycle is to produce useful energy. Thus, energy introduced as acetyl-CoA was transferred to ATP and the intermediate energy carriers. Both NADH and FADH2 carry energetic electrons that will be used to store energy in ATP. Let's return to the original molecule of glucose and review what became of it. Glycolysis generated 2 molecules of pyruvate, 2 ATPs, and 2 NADHs. The 2 pyruvates entered oxidative decarboxylation and produced 2 acetyl-CoA molecules, 2 carbon dioxide molecules, and 2 more NADH molecules. Since 2 acetyl-CoAs are engaged in the Krebs cycle, think of the cycle turning twice. We'll add the final products: 6 CO2, 10 NADH, 2 FADH2, and 4 ATP molecules. Now let's do what we usually do with waste. Get rid of the carbon dioxide. So up to this stage in cellular respiration, glucose has produced 4 power-packed ATPs and 12 impatient energy carriers. In the next program, we'll watch these intermediate energy carriers deliver the payload of ATP.